All the planets and moons we are aware of, both within our own solar system and those light years out, have atmospheres that are distinct from Earth's. Its 4.7 billion years of evolution were influenced by a variety of factors, including the sun's vicinity and the emergence of photosynthetic life. Our world would be lifeless without our beloved atmosphere, roasted by the sun's intense radiation during the day and icy cold at night. To see what happens to a planet when the majority of its atmosphere is lost to space over ages, one simply has to go to Mars. I'll be examining some of the characteristics that make the air we breathe remarkable in this video. A layer, or layers, of gases that surround a planet and are held in place by the gravity of the planetary body is known as an atmosphere. When the gravity is strong and the temperature of the atmosphere is low, a planet preserves its atmosphere. The outer part of a star, which includes the layers above the opaque photosphere, is known as the stellar atmosphere. Low-temperature stars may have outer atmospheres with complex molecules. Nitrogen makes up 78% of the atmosphere of Earth, along with oxygen, 21%, argon, 0.9%, carbon dioxide, 0.04%, and trace gases. The majority of species need oxygen for respiration, while plants, algae, and cyanobacteria use carbon dioxide for photosynthesis. Lightning and bacteria fix nitrogen to create ammonia, which is then used to synthesize nucleotides and amino acids. The atmosphere's stratified structure reduces the negative effects of sunlight, UV radiation, the solar wind, and cosmic rays to shield living things from genetic deterioration. The biochemical change of the paleoatmosphere by living species over billions of years is what led to the makeup of the Earth's atmosphere as it is now. The Earth's atmosphere is made up of layers with various characteristics, such as a particular gas composition, temperature, and pressure. The lowest part of the atmosphere is called the troposphere. This covers the entire world, down to the stratosphere's base. The atmospheric layer where weather occurs, the troposphere, includes 75 to 80% of the mass of the atmosphere. Its height ranges from 17 kilometers at the equator to 7.0 kilometers at the poles. The ozone layer is found in the stratosphere, which stretches from the tropopause to the mesopause and is located between 15 and 35 kilometers above the surface of the Earth. The majority of the UV energy that Earth receives from the sun is absorbed by the atmosphere. Most meteors burn up in the mesosphere, which has a range of 50 to 85 kilometers before they reach the surface. The bottom of Earth's atmosphere is defined by land and water, or the planet's surface. Radiation, conduction, and convection are the three physical processes that heat this surface. As a result, the temperature at the surface's interface with the environment rises. The intensity of solar insolation, the physical properties of the surface, and the wind, temperature, and moisture structure in the atmosphere immediately above the surface all influence each process' relative contributions. The temperature at this interface plays a crucial role in figuring out how favorable a place is for various sorts of life. Electromagnetic radiation, which is generally classified into two types, insolation from the sun and emittance from the surface and atmosphere, affects the temperature of the atmosphere and surface. Shortwave radiation is a term that is usually used to refer to solar radiation, which mainly falls within the ultraviolet and visible regions of the electromagnetic spectrum and mainly has wavelengths between 0.39 and 0.76 micrometers. There was no oxygen in the air until around 2.4 billion years ago. Nevertheless, microscopic life, including photosynthesizing cyanobacteria, was well documented. These creatures, which are also responsible for producing green algae, changed the atmosphere of the planet by producing oxygen through photosynthesis. Before the Great Oxygenation event, oxygen was kept from entering the atmosphere by water, which retained it as it produced rust from iron deposits. The majority of life at the period was anaerobic, meaning that oxygen can be hazardous. Thus, this event caused the first mass extinction on Earth while also making the Earth habitable for us today. While CO2 levels have increased by 60% due to human activities since the beginning of the Industrial Revolution, the greenhouse effect has historically been far higher than it is now throughout the most of Earth's history. CO2 levels were 11 times higher than they are today during the Cambrian period, which witnessed one of the largest evolutionary radiations in history. As a result, the Earth was 7 degrees Celsius warmer, the poles had lost all of their ice, and sea levels were significantly higher. They were still nearly 5 times greater than they are today when the final dinosaurs roamed the Earth hundreds of millions of years later. But eventually, the planet began to cool, ushering in the current Quaternary Ice Age. The sky ought to be purple. The Rayleigh scattering phenomenon, so named for the British physicist who originally explained it in the 19th century, is what causes the sky to be blue. Every color in the visible spectrum is represented by the sun's light, but the atmosphere scatters shorter wavelength colors like blue and violet so that they overshadow longer wavelength colors like red and orange. But shouldn't we all be seeing the sky as purple as violet has the shortest wavelength of any color? Our physiology determines why we see blue instead of purple, since the human eye is more receptive to blue light than violet. 6,200 miles are covered by the atmosphere in space. There are 5 levels to the atmosphere of the Earth. The troposphere, stratosphere, mesosphere, thermosphere, and exosphere are listed in order from lowest to highest. From about 430 miles, 700 kilometers above sea level to about 6,200 miles, 10,000 kilometers, the outermost layer is present before giving way to the solar wind. Because the few gaseous particles in the exosphere are still gravitationally connected to Earth, it is nevertheless regarded as a component of the atmosphere. The thermosphere, the lowermost layer of the atmosphere, is thought to be the uppermost layer by some scientists. The International Space Station is located in the thermosphere in low Earth orbit. Oxygen concentrations were once much higher. The oxygen found on Earth is a byproduct of photosynthesis. Large plants were absent, hence oxygen levels were low even after the Great Oxygenation Event. However, oxygen levels began to soar as life began colonizing the planet during the Devonian period in the form of enormous swamp forests. They attained a level of 32.5% during the Carboniferous, almost 300 million years ago, which was their highest ever. Nature had run amok, creating a volatile environment where forest fires would have been common, blazing for days in the high oxygen atmosphere and turning the sky a bruised scarlet color. All terrestrial life has adapted to a tolerable air pressure of 1 atmosphere, or the temperature at which water boils, on Earth. Air pressures and boiling points decrease as height rises. At 29,000 feet, 9,000 meters, or the summit of Mount Everest, water boils at 72 degrees Celsius. The so-called Armstrong limit, where the air pressure decreases to a level that is lethal without a pressurized suit, is located at an elevation of around 60,000 feet, 18,000 meters. This is due to the fact that biological fluids, including blood and saliva, boil at 37 degrees Celsius, the typical body temperature. It should come as no surprise that this usually results in instant death. Everyone is aware that the air gets colder the higher you go, however the thermosphere really has the warmest temperatures. On the other hand, the coldest place on Earth is at the boundary between the mesosphere and the thermosphere, about 62 miles, 100 kilometers above sea level, where it is a chilly minus 100 degrees Celsius. The thermosphere, on the other hand, experiences the largest temperature variations of all, occasionally reaching a top of 2,500 degrees Celsius. However, the area is nearly vacuum, so it wouldn't feel warm. Intense sun radiation, which would be lethal to life on Earth if it weren't for our atmosphere, is to blame for the high temperatures. Our atmosphere protects us from the hostile expanse of the great beyond, shielding us from deadly sun radiation, low pressures, and extreme temperatures. Fortunately, the atmosphere also shields us from impact events, a different kind of calamity. Nearly all meteorites and space debris that contact the Earth are burned up by the atmosphere. This is brought on by atmospheric friction, which causes smaller things to burn at 1,650 degrees Celsius temperatures. Of course, as the dinosaurs discovered 66 million years ago, there are other objects that are too big or moving too quickly for the atmosphere to burn up before they impact the surface. Water has the most significant effects on the evolution of life as we know it of all the chemicals on Earth. Nothing on the planet can survive without water, yet our atmosphere and distance from the sun also contribute to keeping the temperature of water near its triple point. As a result, water can exist in the forms of a solid, liquid, or gas. At any given time, the atmosphere contains an average of over 40 trillion gallons, 150 trillion liters, of water, which is enough to cover the entire globe with an inch, 2.5 centimeters, of rain. Although it may seem like a significant amount, atmospheric water vapor only makes up 0.001% of all the water on Earth. Would you like to add any more information on the Earth's atmosphere? If so, tell me in the comments section. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.